So good afternoon to everyone. I am Eleonora Tagliabue. I'm a third-year PhD student from Altair Robotics Lab at the University of Verona. And in my presentation today, I will talk about my latest research work, which is about learning the anatomical attachments from simulation data. So this work falls within one of the main research fields that we are working on in my lab, which is surgical robotics. And in particular, my PhD project is within the autonomous robotic surgery project, where the aim of this project is to have the Da Vinci research kit execute representative surgical intervention in complete autonomy on a patient-specific phantom. And when I say autonomously execute the intervention, I don't only mean that the robot has to move without being controlled by the surgeon, but the robot also has to be able to plan the actions to make and also to make decisions based on the current status of surgery. So the specific kind of intervention that we are targeting in ARS project is partial robotic nephrectomy, whose aim is to identify and remove a kidney tumor. So one of the first challenges during the first stages of this procedure is that the kidney is surrounded by adipose tissue, and this adipose tissue prevents direct access to the tumor. So what the surgeon usually does in this situation is to manipulate the adipose tissue, identify where the attachment points are, and then resect the adipose tissue in correspondence to those points. So if we imagine an autonomous agent that has to perform this kind of task, it should know where these attachment points are. But actually, this kind of information is not something that can be extracted from preoperative data. So the robot has to understand where these points are from during the surgery itself. So understanding and estimating where the attachment points are is relevant in autonomous surgery for two main reasons. First of all, because we can direct the robot motion more precisely in order to perform these resection tasks. And as a second point, it also allows to improve the simulation accuracy. Indeed, attachment points act as boundary conditions in biomechanical simulations. And in the context of autonomous surgery, it's very important to have an accurate and up-to-date biomechanical model of the current surgical environment, since all the actions are tested in simulation before being executed on the real system. So the method we propose to solve this challenge is to exploit convolutional neural networks to learn the location of these attachment points from the kind of data that we can acquire during surgery, which is basically a partial view of the deformed surface. And we want to do this without relying on any a priori assumption about the location of these points. And exploiting convolutional neural networks allows us to have very fast prediction, so compatible with intraoperative time. And in addition, in order to cope with the lack of data that we usually have in the medical field, we decided to train this network generating synthetic data from finite element simulations. So here is a very short overview of the pipeline used for data generation. So we started by generating a series of random surface meshes which mimic the adipose tissue, so which have one dimension which is much smaller with respect to the other two. Then we used SOFA here to simulate a series of deformations to this adipose tissue by applying every time a new random force and using a random configuration of boundary conditions, so attachment points. And then as a final stage, we extracted from the deformed configuration a partial surface, which basically plays the role of the partial intraoperative surface that we see during surgery. So in order to exploit convolutional operators, what we had to do at this point was to encode this information into a 3D grid. So we performed an operation which we called voxelization in order to encode in this grid the preoperative undeformed model and the displacement of the points which are visible. Then this represents the input to our network, which is a UNet architecture. And then it provides as output a binary map of the fixed points. So we trained this network with the synthetic data, and then we evaluated its performance in two main fields. So first, we wanted to evaluate the localization accuracy, and we did it by calculating the dice coefficient and the true positive rate. And then as a second metric, we wanted to compute if we could improve also the simulation accuracy. So we computed the maximum volume error. This error is basically obtained by running a forward simulation using as attachment points the boundaries which were predicted by the network and computing the mean square error between the deformed configuration obtained in this case with the ground truth deformed state. So here are some results that we obtained on synthetic samples. And as you can see, both the dice coefficient and the true positive rate are quite high. So the network learned to predict where the attachment points are located. And so if we consider the maximum volume error, so its median value is around 7 millimeters, and it might seem quite high, but we have to consider that in this case, part of this error is due to the fact that these forward simulations obtained with the predicted boundaries are obtained by imposing as input a displacement, while the deformed configuration obtained during data generation time are obtained using an input force. So part of this error is due to the different input method. One of the most important results that we obtained in this case is the prediction time, which is in the order of 40 milliseconds. So it's compatible with intraoperative applications. So we also performed some experiments on real-world phantom data. In particular, we manufactured phantoms with different shapes and thicknesses, and we manipulated them with the DaVinci Research Kit using different configuration of attachment points and from different grasping points. And we acquired data from the deformed configurations with an RGBD sensor. Here are briefly the results we obtained on this real data. So you can see that the true positive rate and the average volume error in this case are really quite comparable to those obtained for synthetic sample. While the dice coefficient here, its median value is a bit lower with respect to synthetic samples. And I just wanted to give you a couple of examples of when this dice coefficient was low. So in the first row, you can see an example of a case where the network overestimated a lot the attached area, and which is represented with so the network prediction is represented in yellow. So, but in that case, in that case, the dice coefficient is very low, but if we go and see how is the deformed configuration with respect to the acquired point cloud, we can see that the shapes fit quite well. And this tells us that actually the network was able to predict the constraint provided by the floor, which is basically acting as a sort of attachment for that phantom. While in the lower row, we can see another case of failure for the network. And this is due to the fact the grasping point in this case is where the green cross is. And our robotic arm was coming from the right-hand side. So most of the input point cloud was occluded. And so this means that point cloud occlusion had a really impact on the prediction accuracy. So to conclude, we have proposed this network which can predict the attachment points and is trained with synthetic data only. And the prediction time takes few milliseconds. So the next steps for this work are about including multiple deformation states as input to the network, which we hope will make the prediction more robust, and then conduct some experiments on more realistic settings. So before concluding my presentation, I just wanted to say a few words about the SOFA awards. So I contributed this year with this tutorial about the different possibilities that are available in SOFA to model the interaction between a soft object and a rigid one. And the reason why I wanted to share this is that I really had a hard time at the beginning when I was working on this project to understand which were the possible options available in SOFA and how they work. And the simulations were really unstable, and there were so many parameters. So I decided to collect a bit the experience that I had, writing also some short documentation. And I just wanted to give a short message, which is everyone can really play a small role and contribute to open source software, even by sharing your experience and some docs or some examples. So just to conclude, I want to conclude with this COVID time picture of my lab, and please feel free to contact me. Here are my details, and thanks for the attention.
Thank you very much, Eleonora, for this very clear presentation. I've got Guillaume in the background telling me that it was a presentation where we could absolutely understand everything. So it's a very good sign.
Okay, thanks for the feedback.
And also quite satisfactory to see that how far you went from from the first SOFA training session and then from now, and even with an open source mentality. So it's marvelous. Is there any question for Eleonora about this work on boundary condition estimation using a convolutional neural network? neural networks. Anyone? I see. Yeah. Jiying is writing. Zara as well. I'll let you guys. Yeah. Okay. What's the pathway to clinical use? How accurate do you need to be?
Well, that's a good question. Let's say that there are two main possible applications of the network, and one is that of identifying where the attachment points are, and in order to do that, we need to be quite accurate, but we also know that we are collecting data with the passing of time. So we can also start maybe with a not really accurate prediction at the first time step, but then while the time is passing, we can improve that prediction. So it shouldn't be accurate from the beginning, but we hope to have to sort of intersect maybe the predictions that we do over time in order to be more and more robust. While from the other point of view, that is on the improvement of the simulation, that really depends on the application and what you need your simulation for. In this case, our aim is to have a simulation which is as accurate as possible, and usually we don't know where the attachment points are in general, so already having a rough guess of where they are can improve it a lot. And
yeah, you noticed the second question. Yeah, did you use SOFA just for providing database for the convolutional neural network? I'm gonna yeah. Go ahead.
Yes, we did. We did use it, but just for that. Actually, that was most of the work.
Convolutional. I need to work on the pronunciation. Okay, great. Thank you, Thank you, G. Thank you, Zara, as well. If there is any additional question, there would be actually a time for question again for Eleonora and for Camille, who is coming right after in the work session that will happen in a few minutes.